cognitive radio is an intelligent radio that can be programmed and configured dynamically. Its transceiver is designed to use the best wireless channels in its vicinity. Such a radio automatically detects available channels in wireless spectrum, then accordingly changes its transmission or reception parameters to allow more concurrent wireless communications in a given spectrum band at one location. This process is a form of dynamic spectrum management. Description: in response to the operator's commands, the cognitive engine is capable of configuring radio system parameters. These parameters include waveform, protocol, operating frequency, and networking. This functions as an autonomous unit in the communications environment, exchanging information about the environment with the networks it accesses and other cognitive radios. A CR monitors its own performance continuously, in addition to reading the radio's outputs. It then uses this information to determine the RF environment, channel conditions, link performance, etc., and adjusts the radio settings to deliver the required quality of service subject to an appropriate combination of user requirements, operational limitations, and regulatory constraints. Some smart radio proposals combine wireless mesh network aerodynamically changing the path messages take between two given nodes using cooperative diversity. Cognitive radio aerodynamically changing the frequency band used by messages between two consecutive nodes on the path. And software-defined radio aerodynamically changing the protocol used by message between two consecutive nodes. J. H. Snyder, Lawrence Lessig, David Weinberger, and others say that low-power smart radio is inherently superior to standard broadcast radio. History: the concept of cognitive radio was first proposed by Joseph Mitola III in a seminar at KTH in 1998 and published in an article by Mitola and Gerald Q. McGuire, Jr. in 1999. It was a novel approach in wireless communications, which Mitola later described as the point in which wireless personal digital assistants and the related networks are sufficiently computationally intelligent about radio resources and related computer-to-computer communications to detect user communications needs as a function of use context, and to provide radio resources and wireless services most appropriate to those needs. Cognitive radio is considered as a goal towards which a software-defined radio platform should evolve. A fully reconfigurable wireless transceiver which automatically adapts its communication parameters to network and user demands. Traditional regulatory structures have been built for an analog model and are not optimized for cognitive radio. Regulatory bodies in the world as well as different independent measurement campaigns found that most radio frequency spectrum was inefficiently utilized. Cellular network bands are overloaded in most parts of the world, but other frequency bands are insufficiently utilized. Independent studies performed in some countries confirmed that observation, and concluded that spectrum utilization depends on time and place. Moreover, fixed spectrum allocation prevents rarely used frequencies from being used, even when any unlicensed users would not cause noticeable interference to the assigned service. Regulatory bodies in the world have been considering whether to allow unlicensed users in licensed bands if they would not cause any interference to licensed users. These initiatives have focused cognitive radio research on dynamic spectrum access. Terminology: depending on transmission and reception parameters, there are two main types of cognitive radio: full cognitive radio, in which every possible parameter observable by a wireless node is considered. Spectrum sensing cognitive radio, in which only the radio frequency spectrum is considered. Other types are dependent on parts of the spectrum available for cognitive radio: licensed band cognitive radio, capable of using bands assigned to licensed users, which will operate on unused television channels. Unlicensed band cognitive radio, which can only utilize unlicensed parts of the radio frequency spectrum. One such system is described in the IEEE 802.15 Task Group 2 specifications, which focus on the coexistence of IEEE 802.11 and Bluetooth. Spectrum mobility, process by which a cognitive radio user changes its frequency of operation. Cognitive radio networks aim to use the spectrum in a dynamic manner by allowing radio terminals to operate in the best available frequency band, maintaining seamless communication requirements during transitions to better spectrum. Spectrum sharing. Spectrum sharing. Cognitive radio networks allow cognitive radio users to share the spectrum bands of the licensed band users. However, the cognitive radio users have to restrict their transmit power so that the interference caused to the licensed band users is kept below a certain threshold. Sensing-based spectrum sharing. In sensing-based spectrum sharing cognitive radio networks, cognitive radio users first listen to the spectrum allocated to the licensed users to detect the state of the licensed users. Based on the detection results, cognitive radio users decide their transmission strategies. If the licensed users are not using the bands, cognitive radio users will transmit over those bands. If the licensed users are using the bands, cognitive radio users share the spectrum bands with the licensed users by restricting their transmit power. Technology. Although cognitive radio was initially thought of as a software-defined radio extension, most research work focuses on spectrum sensing cognitive radio. The chief problem in spectrum sensing cognitive radio is designing high-quality spectrum sensing devices and algorithms for exchanging spectrum sensing data between nodes. It has been shown that a simple energy detector cannot guarantee the accurate detection of signal presence, calling for more sophisticated spectrum sensing techniques and requiring information about spectrum sensing to be regularly exchanged between nodes. Increasing the number of cooperating sensing nodes decreases the probability of false detection. Filling freer F-bands adaptively, using OFDMA, is a possible approach. Timo A. Weiss and Friedrich K. Jundrell of the University of Karlsruhe proposed a spectrum pooling system, in which free bands were immediately filled by OFDMA subbands. Applications of spectrum sensing cognitive radio include emergency network and WLAN higher throughput and transmission distance extensions. The evolution of cognitive radio toward cognitive networks is underway. The concept of cognitive networks is to intelligently organize a network of cognitive radios. Functions. The main functions of cognitive radios are power control. Power control is used for both opportunistic spectrum access and spectrum sharing. CR systems for finding the cutoff level in SNR, supporting the channel allocation and imposing interference power constraints for the primary user's protection respectively. Spectrum sensing, detecting unused spectrum and sharing it, without harmful interference to other users. An important requirement of the cognitive radio network to sense empty spectrum. Detecting primary users is the most efficient way to detect empty spectrum. Spectrum sensing techniques may be grouped into three categories. Transmitter detection. Cognitive radios must have the capability to determine if a signal from a primary transmitter is locally present in a certain spectrum. There are several proposed approaches to transmitter detection: matched filter detection, energy detection. Energy detection is a spectrum sensing method that detects the presence-absence of a signal just by measuring the received signal power. The signal detection approach is quite easy and convenient for practical implementation. To implement energy detector, however, perfect noise variance information is required. And surprisingly, when there is noise uncertainty, there is an SNR wall below which the energy detector cannot reliably detect any transmitted signal. A new energy-based spectrum sensing algorithm with noise variance uncertainty is proposed. This algorithm does not suffer from SNR wall and outperforms the existing signal detectors. And most importantly, the relationship between the energy detector of and that of is quantified analytically. Also, when the noise variance is known perfectly, these two energy detectors achieve the same probability of detection and false alarm rates. Cyclostationary feature detection. This type of spectrum sensing algorithms are motivated because most of man-made communication signals such as BPSK, QPSK, AM, OFDM exhibit cyclostationary behavior. However, noise signals do not experience this behavior. These detectors are robust against noise variance uncertainty. The aim of such detectors is to exploit the cyclostationary nature of man-made communication signals buried in noise. Cyclostationary detectors can be either single-cycle or multi-cycle cyclostationary. Single-cycle detectors: these detectors exploit the existence of the transmitted signal just by considering one cyclic frequency location. Multi-cycle detectors: in this detector, many cyclic frequency locations are examined to detect the presence or the absence of transmitted signals. As this detector considers many possibilities, it usually gives better performance compared to that of the single-cycle detector. But this is at the expense of additional complexity. One low-complexity multi-cycle cyclostationary approach to detect OFDM signals can be found in moment-based detector. Like in the cyclostationary detectors, different man-made signals such as BPSK, QPSK, MAQAM signals also have different n greater than 2th moment values than that of white noise. The moment-based detector exploits this behavior to check the presence or absence of the transmitted signal. To remove the effects of noise variance uncertainty, simple ratio test will work as in wideband spectrum sensing, refers to spectrum sensing over large spectral bandwidth, typically hundreds of megahertz or even several GHz. Since current ADC technology cannot afford the high sampling rate with high resolution, it requires revolutionary techniques, for example, compressive sensing and sub-Nyquist sampling. Cooperative detection refers to spectrum sensing methods where information from multiple cognitive radio users is incorporated for primary user detection. Interference-based detection. Null space-based CR, with the aid of multiple antennas, CR detects the null space of the primary user and then transmit within this null space, such that its subsequent transmission causes less interference to the primary user. Spectrum management, capturing the best available spectrum to meet user communication requirements, while not creating undue interference to other users. Cognitive radios should decide on the best spectrum band to meet quality of service requirements. Therefore, spectrum management functions are required for cognitive radios. Spectrum management functions are classified as spectrum analysis, spectrum decision. The practical implementation of spectrum management functions is a complex and multifaceted issue, since it must address a variety of technical and legal requirements. An example of the former is choosing an appropriate sensing threshold to detect other users, while the latter is exemplified by the need to meet the rules and regulations set out for radio spectrum access in international and national legislation. Cognitive radio versus intelligent antenna. An intelligent antenna is an antenna technology that uses spatial beam formation and spatial coding to cancel interference. However, it is emerging to be extended for an intelligent multiple or cooperative antenna array so as to be applied to the recent complex communication environments. On the other hand, cognitive radio allows user terminals to sense whether a portion of the spectrum is being used to share spectrum with neighbor users. The following table compares the two. Note that both techniques can be combined as illustrated in many nowadays transmission scenarios. Applications can sense its environment and, without the intervention of the user, can adapt to the user's communications needs while conforming to FCC rules in the United States. In theory, the amount of spectrum is infinite. Practically, for propagation and other reasons it is finite because of the desirability of certain spectrum portions. Assigned spectrum is far from being fully utilized, and efficient spectrum use is a growing concern. CR offers a solution to this problem. A CR can intelligently detect whether any portion of the spectrum is in use, and can temporarily use it without interfering with the transmissions of other users. According to Bruce Fett, some of the radio's other cognitive abilities include determining its location, sensing spectrum use by neighboring devices, changing frequency, adjusting output power or even altering transmission parameters and characteristics. All of these capabilities, and others yet to be realized, will provide wireless spectrum users with the ability to adapt to real-time spectrum conditions, offering regulators, licenses and the general public flexible, efficient and comprehensive use of the spectrum. Simulation of CR networks. At present, Modeling and simulation is the only paradigm which allows the simulation of complex behavior in the environment's cognitive radio networks. Network simulators like OpenNet, NetSim and NS2 can be used to simulate a cognitive radio network. Areas of research using network simulators include A. Spectrum sensing and incumbent detection, B. Spectrum allocation, and C. Measurement and modeling of spectrum usage. Future plans. The success of the unlicensed band in accommodating a range of wireless devices and services has led the FCC to consider opening further bands for unlicensed use. In contrast, the licensed bands are underutilized due to static frequency allocation. Realizing that SIA technology has the potential to exploit the inefficiently utilized licensed bands without causing interference to incumbent users, the FCC released a notice of proposed rulemaking which would allow unlicensed radios to operate in the TV broadcast bands. The IEEE 802.22 Working Group, formed in November 2004, is tasked with defining the air interface standard for wireless regional area networks for the operation of unlicensed devices in the spectrum allocated to TV service. See also, channel allocation schemes, channel-dependent scheduling, cognitive network, LTE advanced, network simulator, OFDMA, radio resource management, references. External links. Berkeley Wireless Research Center Cognitive Radio Workshop, a first workshop on cognitive radio. Its focus was mainly on research issues in topic, Center for Wireless Telecommunications, Virginia Tech, Cognitive Radio Technologies Proceeding of Federal Communications Commission, Federal Communications Commission Rules on Cognitive Radio, IEEDY SPAN Conference. It then uses this information to determine the RF environment, channel conditions, link performance, etc., and adjusts the radio settings to deliver the required quality of service subject to an appropriate combination of user requirements, operational limitations, and regulatory constraints. Some smart radio proposals combine wireless mesh network dynamically changing the path messages take between two given nodes using cooperative diversity, posed by Joseph Mitola III in a seminar at KTH in 1998 and published in an article by Mitola and Gerald Q. McGuire, Jr. in 1999. It was a novel approach in wireless communications, which Mitola later described as the point in which wireless personal digital assistants and the related networks are sufficiently computationally intelligent about radio resources and related computer-to-computer communications to detect user communications needs as a response to the operator's commands. The cognitive engine is capable of configuring radio system parameters. These parameters include waveform, protocol, operating frequency, and networking. This functions as an autonomous unit in the communications environment, exchanging information about the environment with the networks it accesses and other cognitive radios. A CR monitors its own performance continuously, in addition to reading the radio's outputs. A cognitive radio is an intelligent radio that can be programmed and configured dynamically. Its transceiver is designed to use the best wireless channels in its vicinity. Such a radio automatically detects available channels in wireless spectrum, then accordingly changes its transmission or reception parameters to allow more concurrent wireless communications in a given spectrum band at one location. This process is a form of dynamic spectrum management. Description: cognitive radio dynamically changing the frequency band used by messages between two consecutive nodes on the path. And software-defined radio dynamically changing the protocol used by message between two consecutive nodes. J. H. Snyder, Lawrence Lessig, David Weinberger, and others say that low-power smart radio is inherently superior to standard broadcast radio. History: the concept of cognitive radio was first